our next speaker is Nadav, Amit from Technion. So if you went to last night's dinner, you probably remember. So Nadav is this year's runner-up to our SIGOps Distinguished Thesis Award. So next he will tell us one of the many interesting things that he has been doing.
Thank you. Hi, I will present a joint work of the Technion University with the Intel, which was conducted by Professor Tsafrir, Professor Assaf Schuster, Ahmad Ayoub, and Eran Shlomo, as well as me. So here is a question, sorry. Assume you have a video server that records surveillance camera streams, yet once a month, your server freezes completely. You are worried it would occur when a thief arrives. What are the possible causes? Well, it might be the operating system, drivers, or BIOS. Perhaps there is some hardware problem. Your system may have been hacked by the thief himself, or if you look for far-fetched reasons, you may consider the effect of cosmic rays or power surge. 10 years ago, these reasons would cover all the possible causes of the problem, pretty much. Yet today we have another possible cause, the hypervisor. Today, 75% of x86 server workloads are virtualized, the vast majority using hardware-assisted virtualization, which allows us to run multiple virtual machines on top of a single physical server. As a result, servers achieve higher hardware utilization, easier manageability, and a bunch of other benefits, which essentially reduce the total cost of ownership. Hardware-assisted virtualization still requires a software layer, a hypervisor, to carry various virtualization tasks. These tasks include trapping and emulating virtual machine instructions and events, and saving and restoring the virtual machine state. Implementing a hypervisor is hard, and bugs in hypervisor code might have implications on the security and stability of virtual machines. In our work, we focus on CPU virtualization. Relative to virtualizing other devices, CPU virtualization is the hardest to implement due to its complexity. CPU virtualization bugs might jeopardize both the host and the virtual machine. The security of the host might be compromised since CPU virtualization is performed in the host kernel space to improve performance. And virtual machines may fail since their operating system code is not built to deal with these virtual CPU bugs. Here is a real-life example. A Zen hypervisor bug, which was found a year ago, caused virtual machine read operations of certain non-existing registers to succeed instead of triggering an exception. Alas, the read operations returned data that wasn't supposed to be accessible to the VM. While there were no known exploits of the bug, cloud vendors, including Amazon, SoftLayer, and Rackspace, had to reboot many virtual machines in order to patch the hypervisors. This process did not go smoothly. For example, 18% of SoftLayer clients reported a downtime of over an hour. Others have tried to address the challenge of providing a bug-free hypervisor which conforms with real hardware. They did it in 3 ways. Micro-hypervisors perform virtualization using a small trusted computing base. Reducing the trusted computing base indeed improves the host security, but it does not eliminate bugs, since micro-hypervisor must provide the same functionality that hypervisors do. Formal verification attempts to provide a proof of hypervisor correctness, yet it is hard to accomplish, and it suffers from many limitations, notably due to the lack of a formal model of the CPU. Hypervisors can also be tested using code fuzzing, running random tests on both a VM and the native system and comparing the results. But previous attempts achieved poor coverage and suffered from high false positive rate. In our work, we address the limitation of existing solutions for hypervisor bugs and specifically of fuzzing techniques. Virtual machines believe they operate on the physical hardware, so the hypervisor must accurately emulate the physical hardware. As it happens, hardware vendors already know how to test this hardware. In fact, they invest heavily, hundreds of person-years, in developing infrastructure for testing the CPU. Our insight is that this infrastructure could be in principle applied to hypervisors, as virtual and physical CPUs should behave similarly. Our contribution is therefore adapting the physical CPU testing infrastructure such that it will work on virtual CPUs. We ran the tools and studied the results. In our study, we found and fixed over 100 bugs in a common hypervisor, and we analyzed these bugs in this presentation. The outline of the presentation is therefore as follows. Following our motivation, I will now present the testing system, first describing the Intel CPU testing tools, and then our adaptations of the tools for testing virtual CPUs. Then I will show hypervisor testing results and analysis of the bug causes and impact. Later, I will discuss architectural CPU flaws that we found which cause virtual CPUs to behave differently than CPUs. Here is how the testing infrastructure of Intel works. In the beginning, the generator generates a random test utilizing intimate knowledge of the x86 architecture. A test is an executable memory image that, upon completion, its result can be compared to those of a reference system to indicate a success or a failure. A test has a fixed initialization and completion code. Its body consists of random instruction and random templates. A template produces behavior that will not happen on its own and requires semantic knowledge. For example, there is a template that generates interprocessor interrupts and later spins until the interrupts arrive. Importantly, the generator works in tandem with an architectural simulator. During the generation of each test, each instruction is executed on the simulator immediately after it is generated. In addition to serving as a reference system for the differential testing, the simulator provides the outcome of executing of each instruction. The generator uses this outcome to mask undefined results of certain instructions and to roll back instructions whose results are undesired. When the test is ready, the loader queues it for execution. The test is then sent using a proprietary device to the system under test, marked here as the SUT. The device loads it to memory and triggers an init event, which initiates a test. When the test completes, the SUT, the system under test memory, is compared to the test device. Is compared by the test device, I'm sorry. And the result is then delivered back to the loader to be recorded. If a test fails, it can be re-executed and debugged using a sophisticated set of tools. The test environment delivers several advantages. First, it gives us a very high coverage, which is achieved using deep architectural semantic knowledge combined with the huge effort that Intel puts into developing those tools. Second, the infrastructure enjoys a low false positive rate because, for example, the generator uses the architectural simulator to mask undefined results, or because it avoids triggering errata that have non-deterministic results, or because it generates asynchronous events in a deterministic manner. Another important advantage is that the tests are made easy to debug. For example, register values are checked at multiple points throughout the test, and the test fails immediately if these values, if the execution diverges from the expected execution. This helps pinpointing the problem sooner. When a test fails or hangs, additional debug information is recorded in memory, and in addition, a detailed trace of the expected architectural execution can be generated to help debugging. To use Intel testing tools in virtual machines, certain adaptations were needed. The first problem we encountered is that the hypervisor we used, KVM, missed several virtualization features. In some cases, the hypervisor worked according to the CPU specifications and reported that these features were unsupported. Yet, some of these features exist in all x86 CPUs for almost 10 years, and their missing support causes problems even for real operating systems. For example, by default, OS 6 cannot run within a virtual machine since KVM does not support cache line monitoring. Our tests relied on some of these features, and we therefore added them to the hypervisor. As for other features, we prevented their use in the test. For example, we didn't use data breakpoints, since KVM does not handle them well. Test execution in virtual machines is done quite similarly to the way it is done on real systems. Yet we need several adaptations. I will describe the main changes. We created a vloader, a virtual loader, that takes the place of the loader. The vloader loads the test directly to the virtual machine memory using the hypervisor monitoring protocol, and uses this protocol also to trigger the init event which starts each test. We enhanced the monitoring protocol to support these events. Curbing OS jitter is a consideration of ours. Now that the tests run within a virtual machine, we still want test failures to be easily reproducible, so that debugging would be possible. We were worried that non-deterministic events in the host operating system would prevent their reproduction, and we therefore used known techniques to curb the OS jitter. Testing I/O devices in real systems required a proprietary test device. We adapted the testing environment for virtual machines by creating an emulated test device which is compatible with the real one. Finally, we enhanced the debug tools that exist for debugging virtual machines. We found the existing tools insufficient since they can affect the test results. In total, the adaptation effort is reasonably low, and most of the complications result from hypervisor bugs and missing virtualization features. We started by running empty tests, which only included fixed code for test initialization and completion, and did not include any random code. Getting such a test to pass took 2 weeks, and an additional month was required to get one random test to pass. The time each test takes is reasonable as well. Generating a test for 2 cores when each core runs 4096 random instruction, which is the default, takes 5 seconds. Since each test image takes roughly 1 megabyte, they can be saved and re-executed for regression testing. Execution of a test takes less than a second, since the virtual machine memory is loaded directly, and since a full virtual machine reset is not required. Debugging of each bug, of each failure, required 3 hours on average per bug. But there is a very high variability in debugging. Debugging of simple bugs can take 15 minutes, but it is much more complicated when bugs are caused by missing documentation or code races. Yet each bug was debugged within a day. Using the testing infrastructure that we adapted for virtualization, we tested the KVM hypervisor. I will now show our results. So the KVM hypervisor that we validated is integrated in Linux and used by cloud providers such as Google. We ran the project for nearly a year, enabling most, not all, of the testing tool features, and found and fixed 117 bugs. You can find almost all of our fixes in the latest Linux kernel. The pie chart here describes the amount of bugs we encountered in the virtualization of each CPU feature. The vast majority of the bugs occurred in the instruction emulator, which I will discuss next. Several bugs occurred in emulating CPU debug features, which were mostly emulated to allow both the virtual machine and the host to debug virtual machine code simultaneously, not something which is commonly done. Some of the bugs were caused by errors in the emulation of CPU reset. Actually, the tests were not intended to find reset bugs, but these bugs caused them to fail. Few of the bugs are attributed to emulating task switch, a legacy CPU mechanism which is not natively virtualized. Several bugs were found in the virtualization of model-specific registers, and one of them caused the host to crash. Emulating the local epic, which is a component of the interrupt controller, caused several bugs, some of which resulted in spurious or missing interrupts. As we just saw, the instruction emulator of KVM caused most of the bugs. Actually, some find it quite surprising that a hypervisor needs to employ a comprehensive instruction emulator when using hardware-assisted virtualization. They assume that most of the instructions should run natively on the CPU. There are 3 main reasons for instruction emulation, but nowadays it is mainly used to emulate I/O instructions. When the virtual machine runs an instruction that accesses I/O ports or memory, the instruction is trapped before it is executed. The hypervisor then needs to emulate the instruction in order to determine which device port or memory are accessed, and only then it is able to emulate the I/O device response. To thoroughly test the instruction emulator, we added to KVM a special stress mode in which each instruction whose emulation is supported by the hypervisor is indeed emulated. In this mode, when the hypervisor encounters an instruction whose emulation is unsupported or needs to inject an interrupt to the virtual machine, we run a single instruction natively in the virtual machine and then continue instruction emulation afterwards. In the previous pie chart, we saw the breakdown of CPU bugs according to the CPU feature whose virtualization was broken. We now look at the bug causes as we analyze them. The vast majority of the bugs occurred since the hypervisor developers did not follow specifications carefully enough. In 7% of the cases, however, we cannot fully blame the developers, since the documentation was either not clear enough or even completely missing. In one of the cases, we could not find the CPU behavior documented anywhere, not even in any esoteric blogs. And then in another case, the documentation was recently fixed. The rest of the bugs, according to our analysis, were caused by coding error, races, null dereferences, wrong error codes, and so on. Next, we are interested in the impact of the bugs, and we will start with security. We found 6 security vulnerabilities that the bugs caused. Hypervisor vulnerabilities can be categorized as those that compromise the host or just the virtual machine. 3 of the bugs we found compromised the host, as they caused it to crash, and could therefore be used for denial of service attack on the host. Moving hypervisor code to user space can improve the host security, and in theory could eliminate all those vulnerabilities. Yet we found 3 other vulnerabilities in which the guest security is compromised, allowing unprivileged virtual machine code to crash the entire virtual machine or gain higher privilege. Cloud providers may not be concerned about such bugs since they do not compromise their infrastructure, yet cloud clients should be worried since their security is compromised. Unsurprisingly, the bugs that caused most of these vulnerabilities were instruction emulator bugs. The instruction emulator code is very complicated, as the x86 instruction set consists of over 800 instructions. In fact, on most setups, many instructions should not be emulated, yet their emulation is not prevented. If a bug exists in the emulation of almost any instruction, a malicious virtual machine code can trick the hypervisor into emulating it. Here is an example. Our tests revealed that there is a bug in the emulation of the sysenter instruction, which performs a fast entry to the kernel. The bug elevated under certain conditions the virtual machine privilege level without jumping to the kernel entry point correctly. User space code can therefore gain kernel space privilege level if sysenter instruction is emulated. Sysenter instruction is usually not wrapped and emulated, so we need to trick the hypervisor into emulating this instruction in order to exploit the bug. How can we do so? Well, Linux usually grants user space read access of the HPET, the high precision timer, in order to speed up the execution of the get time of day system call. We start by running an instruction that reads the HPET. As a result, the hypervisor traps the instruction since the HPET that the virtual machine accesses is emulated. The hypervisor needs to fetch and decode the trapped instruction before emulating it. And this leaves us a small window of time that another virtual CPU can rewrite the instruction and set another instruction, sysenter in our case, instead of it. The hypervisor would then fetch and emulate the sysenter instruction, and the vulnerability would be exploited. Another implication of hypervisor bugs is reduced virtual machine stability. 2 of the bugs we encountered were also reported by the KVM hypervisor users. The effect of one of these bugs was described on the first slide. A Windows XP virtual machine that ran a video server froze once a month and started working again when the user opened the virtual machine console. The KVM team tried to analyze the root cause of this bug for over a month without success. Eventually, the problem turned out to be caused by one of the bugs we encountered, whose fix was not backported to the failing hypervisor version since nobody suspected it happens on real systems. This bug actually existed in KVM code for nearly 5 years. And one of the users who complained about it indicated that he encountered this bug several times over the years. In addition, we encountered 4 other software regressions, bugs that were caused by enhancements or other bug fixes. These bugs were suspected to happen in real systems, and their fix was backported to old KVM versions. Besides hypervisor bugs, we also encountered 4 virtualization hardware flaws. How do we define such flaws? Popek and Goldberg defined the properties that virtual machines should fulfill. The first 2 are equivalence. The virtual machine should behave the same as if it was running without virtualization, excluding timing. And second, efficiency. The virtual machine should run innocuous instructions directly on the CPU, without requiring the hypervisor to trap and emulate them. However, we encountered several discrepancies between CPU and virtual CPU, which we could not fix in software without potentially trapping innocuous instructions. In other words, we need to either sacrifice equivalence or efficiency. We attribute this limitation to CPU architecture deficiencies. We find 3 causes for these deficiencies: non-virtualizable state, missing state-save restore facilities, and CPU errata, which affects virtual machines differently than native systems. Here is one example of such architectural flaw with real implications. When a floating point unit instruction faults, the CPU updates 2 internal registers to indicate the faulting instruction. FCS holds the segment selector of the instruction, and FIP holds a 32 or 64-bit offset in that segment. Unprivileged instructions can be used to examine the registers by storing their value in memory. The problem is that hypervisors cannot restore the virtual machine FPU state correctly. The instruction set only enables to either load the FCS and a 32-bit FIP, or load a 64 FIP and 0 FCS. Sorry. This caused our tests to fail on old Intel CPUs that we used during the development. And we found that this discrepancy was reported before, as it caused the blue screen of death on certain Windows systems. Yet, in addition to the known problem, our tests reveal another one, which was previously unknown. It turns out that the new Intel CPUs solved the previous discrepancy by deprecating FCS, by deprecating saving FCS to memory. So FCS is always read by the user as 0. Now, as a result, code that runs in legacy execution mode, which is called real mode, may read the wrong FIP, which in this mode is calculated as a byproduct of the internal FCS and FIP. You can find the full details of this problem in the paper. To conclude, the number and the severity of the bugs we have found show that virtualization robustness and security cannot be taken for granted. Efficient testing of hypervisor is required, and our results show that CPU vendors are capable of delivering it. We further believe that it's in their best interest, since hypervisors are nowadays an integral part of server ecosystems, and most workloads run on virtual CPUs. We think it may be a good idea for CPU vendors to certify hypervisors that pass their tests, similarly to the way Microsoft certifies device drivers. As we finalized our project, we have handed off the testing infrastructure to Intel Open Source Technology Group. Yet it appears a management decision is required for x86 hypervisor testing to be performed on a regular basis. Thanks, and I'll be happy to answer your questions.
Ed Bugnon, EPFL. So first of all, truly great work. Certainly wish I had the test suite 15 years ago. And it's actually nice to see that this is a case of good collaboration between industry and academia, because those test suites were certainly held very close to the chest by the CPU vendors until very recently. So I guess my question is about the equivalence and the equivalence goal. And when VTX was introduced, the goal was, or the idea was that you could build a VMM that was going to be both sound and complete, right? It would be sound in that it would be perfect, and it would be complete in that you could actually run any guest operating system and any hardware configuration in the VMM. And I guess your work shows that we cannot have soundness and completeness. And the specific question, is it possible to actually improve the soundness of the virtualization substantially, potentially at the expense of the completeness of the virtualization?
I might have not, thank you for the compliments, but I may not have completely understood your question. So if you want me to answer something.
No, I'll just rephrase it. So the emulator exists for completeness. And as you said, the emulator is incredibly complex, and I believe nobody believes that the emulator, even having fixed 117 bugs, is now necessarily perfect.
Yeah.
So the question is, can you get rid of the emulator, and what is the drawback of getting rid of the emulator potentially at the expense of the completeness of the virtualization?
Yes. So I think that you can get rid of the emulator if you either improve the instruction set or the architecture. For instance, you do not want the emulator to need to decode the instruction again. The CPU could decode it for it without requiring it to re-decode the instruction. I think that there is no awareness, let's say, in Intel, my feeling, about the need to give something, to make commitment to have something which is sound enough. And I think the instruction set cannot be simplified, but new CPUs can say, whenever you do I/O, you do it with a certain one instruction instead of a complicated set of instructions. And then you would have an operating system which would use for I/O a much simpler interface. I don't think it will come in a high cost. And it's kind of a power virtualization in a way, you may say. But I think that currently, yes, the instruction set is so complicated, I don't know how to simplify it in very high.
Thank you.
Thank you.
Hi, Stephen Sherrod from Data61. So you said that it took about 5 seconds to generate a random test and then an additional second to actually run the test. How long should I spend testing my hypervisor like this before I get a reasonable degree of confidence that it is correct?
So we executed over 100,000 tests. And eventually, let's say that I cannot give you a number of confidence, but we pretty much ran out of bugs, excluding the instruction emulator, which is just buggy as hell, okay? We fixed many bugs, but there are so many others that the fix was just too intrusive for us to implement. So I think that at this point you can say that we did not test many of the subsystems of the CPU, for example, external interrupts, we did not enable it. So I think that you can say that right now the subsystems that we checked are okay. But again, we did not check everything.
Thanks.
Okay, I'm just correction, okay according to the testing tools. Of course, they are not perfect.
Hello, Derek from Apple. Great and valuable work. I think it's really going to pay off in terms of real-world security and stability benefits. One thing I was curious about, and possibly a future avenue for investigation, have you ever tested system management mode and transitions to and from SMM? Because that's one of the most worrisome features of the Intel architecture, and if any kind of privilege escalation to SMM mode is possible, that's a perfect malware vector.
So we did not test it, and the reason we didn't test, other than some complications that might happen, is because KVM did not support SMM at the time. Right now, KVM started supporting it just recently after our project was done.
Great. I look forward to hearing more about that.
Hi, I'm Nathan Pemberton from UC Berkeley. You said you found 100-ish bugs in your time on the current version of KVM that you were working with. Do you have a sense of how many bugs, did you go back to look at old bug reports, how many bugs you would have found that they found through other channels? Like what proportion of bugs do you think you're finding?
Okay, so we checked KVM versions 3.14 till 3.18, something like that. And I looked back at bug reports, Now I know what the testing what are the limitations of the testing. So I don't look at, let's say, timestamp counter that we did not test, okay? So excluding those subsystems that we did not test, I saw no bug reports that we missed. So that's all I can say. Obviously, it's not perfect. We know about some limitations of the testing tools, especially in regard, for instance, for task switch. There is some mode of task switch which is called 16-bit task switch. I don't know if anyone ever used it. And this one is not exercised by the tests.
Thanks.